Hello everyone, this is Srijit and welcome to the subject MCA C35 Advanced Database Management Systems. Today we will discuss the topic data mining, in which we briefly cover applications of data mining, different classifiers, associations and its rules, and clustering. First, let's see what is data mining. Data mining is the process of semi-automatically analyzing large databases to find useful patterns. Like knowledge discovery in artificial intelligence, also called machine learning or statistical analysis, data mining attempts to discover rules and patterns from data. However, data mining differs from the machine learning and statistics in that it deals with large volumes of data stored primarily on disk. That is, data mining deals with knowledge discovery in databases. Let's see the applications of data mining. First one is the prediction based on past history. For example, predict if a credit card applicant poses a good credit risk based on some attributes like income, job type, age, etc., and past history. Or predict if a pattern of phone calling card usage is likely to be fraudulent or mail as spam. Then we have classifications. So given a new item and whose class is unknown, and in classification we predict to which class it belongs. Then we have regression formulae. Given a set of mappings for an unknown function, predict the function result for a new parameter value that we are giving. Then another class of applications looks from associations. Here, associations is like, for example, find books that are often bought by similar customers. If a new such customer buys one such book, suggest the others too. And association may be used as a first step in detecting causation. For example, a certain chemical X can induce cancer or it can cause cancer. Then we have clusters. For example, typhoid cases were clustered in an area surrounding a contaminated well. Or detection of clusters remain important in detecting epidemics, as all of you know and aware of the current COVID-19 scenario in our state and formation of clusters, etc. Associations and clusters are examples of descriptive patterns. As we saw earlier, prediction is one of the most important types of data mining. We describe classification, study techniques for building one type of classifiers called decision tree classifiers, and then study other prediction techniques. Abstractly, the classification problem is this. Given that item belongs to one of several classes and given past instances called training instances of items along with the classes to which they belong. The problem is to predict the class to which the new item belongs. The class of the new instance is not known, so other attributes of the instances must be used to predict the class. Then we can see the classification rules. The classification rules help assign new objects to classes. For example, given a new automobile insurance applicant, should he or she be classified as low risk, medium risk, or high risk? Classification rules for above example should use a variety of data such as educational level, salary, age, etc. See in this case, for every person P, if P dot degree is equal to master's and P dot income is greater than 75,000, P's credit is excellent. Or for all persons P dot degree is equal to bachelor's and P's income is greater than or equal to 25,000 and P's income is less than or is equal to 75,000. That is, P's income is in between 25,000 and 75,000. Then we can say P's credit is good. Rules are not necessarily exact. There may be some misclassifications, and classification rules can be shown compactly as is the decision tree, like the one we are going to see in the next slide. So let's see the decision tree classifier. Here we can see the tree with the degree as root, and we have income nodes and some branches which shows bad, good, and average. Let's see what it is. The decision tree classifier is a widely used technique for classification. As the name suggests, a decision tree classifier uses a tree. Each leaf node has an associated class, and each internal node has a predicate, or more generally, a function associated with it. To classify a new instance, we start at the root and traverse the tree to reach a leaf. In an internal node, we evaluate the predicate or the function of the data instance to find which child to go to. The process continues until we reach a leaf node. For example, if the degree level of a person is master's and the person's income is 40K, starting from the root, we follow the edge label master's, and from there the edge label 20K to 75K to reach a leaf. The class at the leaf is good, so we predict that the credit risk of that person is good. Now let's see how to build a decision tree. Before that, a training set is a data sample in which the classification is already known. And most common way of building a decision tree is to use a greedy algorithm which works recursively, starting at the root and building the tree downward. Initially, there is only one node, the root, and all training instances are associated with that particular node. Each internal node of the tree partitions the data into groups based on a partitioning attribute and a partitioning condition for the node. The data associated with each child node is the set of training instances that satisfy the partitioning condition for that child node. In our example, the attribute degree is chosen and 4 children, one of each value of degree, are created. Let's see the leaf node. And the leaf node, all or most of the items at the node belongs to the same class, or all attributes have been considered and no further partitioning is possible. So this is how the tree is built from the root, and we are creating child based on certain conditions, and we will at the end we will reach at certain leaf, which is the end nodes, where we conclude it, or we classify the particular item, or we can't further classify it, or further partitioning is not possible. By choosing a sequence of partitioning attributes, we start with a set of all training instances, which is impure in the sense that it contains instances from many classes, and ends up with leaves which are pure in the sense that at each leaf all training instances belongs to only one class. So we'll pick best attributes and conditions on which to partition. The purity of a set S of training instances can be measured quantitatively in several ways. And one of the measure is Gini measure. The Gini measure of purity is defined as Gini of S is equal to 1 minus summation from I minus 1 to k pi square, where k is the number of classes and modular S is the number of instances, and pi is a function of instance in class I. When all instances are in the same class or a single class, the Gini value is 0. It reaches its maximum of 1 minus 1 by k if each class the same number of instances. Another measure of purity is the entropy measure, which is defined as entropy of S is equal to minus of summation of I minus 1 to k pi log pi to the base 2. When a set of S is split into multiple sets, say Si, where I is from 1 to 2 to R, we can measure the purity of the resultant set of sets as purity of S1, S2 to Sr is equal to summation from I equal to 1 to R modulus of Si divided by modulus of S into purity of Si. The information gain due to particular split of S into Si, where I is from 1 to R, the information gain of S set of S1 to S2 to Si is equal to purity of S minus purity of set S1, S2, etc. to Sr. The measure of cost of a split is defined as information content. So the information content of S to the set S1, S2, etc. to SR is defined as minus of summation of I minus 1 to R modulus of Si divided by modulus S into log of S modulus of Si divided by modulus S to the base 2. The information gain ratio is the information gain of S2 set Si, S2, etc. SR divided by the information content of S2 set S1, S2, etc. to SR. The best split is the one that gives the maximum information gain ratio. So based on this maximum gain information ratio, we can have best splits, or we'll split based on that. Next, let's see how to find the best splits. Attributes can be either continuous valued, that is, the values can be ordered in a fashion meaningful to classification, such as age or income, or they can be categorical, that is, they have no meaningful order, such as department names or country names. So these categorical attributes can be split multi-way, one child for each value, or can be binary split, that try all possible breakup of values into two sets and pick the best. In case of continuous valued attributes, so we can binary split it. So sort values, try each as a split point. For example, if values are 1, 10, 15, 25, split at less than or equal to 1, less than or equal to 10, less than or equal to 15, like that. And pick the value that gives the best split. Or in multi-way split, a series of binary splits on the same attribute has roughly equivalent effect. To find the best binary split of a continuous valued attribute, we first sort the attribute values in the training instances. We then compute the information gain obtained by splitting at each value. For example, if the training instance have values 1, 10, 15 and 25 for an attribute, the split points considered are 1, 10, 15, and in each case values less than or equal to the split point from one partition, and the rest of the values form the other partition. The best binary split for the attribute is the split that gives the maximum information gain. For a categorical attribute, we can have a multi-way split with a child for each value of the attribute. This works fine for categorical attributes with only a few distinct values, such as degree or gender. However, if the attribute has many distinct values, such as department names in a large company, creating a child for each value is not a good idea. In such cases, we would try to combine multiple values into each child to create a smaller number of children. Now let's see the decision tree construction algorithm. The main idea of decision tree construction is to evaluate different attributes and different partitioning conditions and pick the attribute and partitioning condition that results in the maximum information gain ratio. The same procedure works recursively on each of the sets resulting from the recursion resulting from the split, thereby recursively constructing a decision tree. If the data can be perfectly classified, the recursion stops when the purity of the set is 0. However, often data are noisy or a set may be so small that partitioning it further may not be justified statistically. In this case, the recursion stops when the purity of the set is sufficiently high and the class of the resulting leaf is defined as the class of the majority of the elements of that set. In general, different branches of the tree could grow to different levels. So let's see the procedure. Procedure is like that. The procedure grow tree of S. First we call the function partition S. So the procedure partition S is like this. If purity of S is greater than delta P or modulus S is less than delta S, then return. Else, for each attribute A, evaluate splits on attribute A. Use best split found across all the attributes to partition it. S into S1, S2, etc. to SR. For I equal to 1 to R, partition Si. So the function is recursive. It will continue until it is classified or no further classification is possible. Several of the algorithms also prune subtrees of the generated decision tree to reduce overfitting. Pruning means will remove the subtrees. Okay, so a subtree is overfitted if it has been so highly tuned to the specifics of the training data that it makes many classification errors on other data. A subtree is pruned by replacing it with a leaf node. So we'll cut that subtree and replace it with a leaf node. Now let's see other types of classifiers. Bayesian classifiers find the distribution of attribute values for each class in the training data. When given a new instance D, they use the distribution information to estimate for each class Cj the probability that instance D belongs to a class Cj denoted by PCJD in a manner outlined here. The class with maximum probability becomes the predicted class for instance D. So the Bayesian classifiers use Bayes' theorem, which says probability of instance D being in class Cj is the product of probability of generating instance D given class Cj and the probability of occurrence of class Cj divided by the occurrence probability of instance D. Thus, the Bayesian classifiers require computation of PDCJ, which is the probability of generating instance D given class Cj, and pre-computation of PCJ, which is the probability of occurrence of class Cj. The PD can be ignored since it is the same for all classes. To simplify the task, naive Bayesian classifiers assume attributes have independent distributions and thereby estimate PDCJ as a PD1CJ into PD2CJ into P etc. to PDNCJ, where each of the PDICJ can be estimated from a histogram on DI values for each class CJ. The histogram is computed from the training instances. So histograms on multiple attributes are more expensive to compute and store. Okay. Significant benefit of Bayesian classifiers is that they can classify instances with unknown and null attribute values. Unknown or null attributes are just omitted from the probability computation. In contrast, decision tree classifiers cannot meaningfully handle situations where an instance of the classified has a null value for a partitioning attribute used to traverse further down the decision tree. Now let's see regression. A regression deals with the prediction of a value rather than a class. Given values for a set of variables x1, x2, etc. to xn, we wish to predict the value of a variable y. One way is to infer coefficients a0, a1, etc. to an such that y is equal to a0 plus a1 into x1 plus a2 into x2 plus etc. plus an into xn. Finding such a linear polynomial is called linear regression. In general, the process of finding a curve that fits the data into are called curve fitting. The fit may only be approximate because of the noise in the data or because of the relationship is not exactly a polynomial. So regression aims to find coefficients that gives the best possible fit. So regressions, they are not for classification but for finding or predicting a value. Now let's see how a classifier is validated. It is important to validate a classifier, that is to measure its classification error rate before deciding to use it for an application. Let's take a case of a test for a disease. A set of test cases where the outcome is already known is used to measure the quality, that is the error rate of the classifier. A true positive is a case where the prediction was positive and the person actually had the disease, while a false positive is a case where the prediction was positive but the person did not have the disease. True negative and false negative are defined similarly for the case where the prediction was negative. Given a set of test cases, let TPOS, FPOS, TNEG and FNEG denote the number of true positives, false positive, true negatives and false negatives generated. Let POS and NEG denote the actual number of positives and negatives. It is easy to see that POS is equal to T post plus F neg and neg is equal to F post plus T neg. The quality of classification can be measured in several different ways. First is accuracy, which is defined as T post plus T neg divided by post plus neg. That is the fraction of the time when the classifier gives the correct classification. Second one is recall, also known as sensitivity. It is defined as T post divided by post. That is how many of the actual positive cases are classified as positive. Third one is the precision, defined as T post divided by T post plus F post. That is how often the positive prediction is correct. And finally, we have specificity, that is defined as T neg divided by neg. Now, which of these measures should be used for a specific application depends on the needs of that application. For example, a high recall is important for a screening test, which is to be followed up by a more precise test, so that patients with the disease are not missed out. In contrast, a researcher who wants to find a few actual patients of the disease for further follow-up but is not interested in finding all patients may value high precision over recall. Different classifiers may be appropriate for each of these applications. Now let's see what is cross validation. In cross validation, the available test cases are divided into k parts numbered 1 to k, from which k different test sets are created as follows. Test set I uses the ith part of validation. After training the classifier using the other k-1 parts, the results T post, F post, etc. from all k test sets are added up before computing the quality measures. Cross-validation provides much more accurate measures than merely partitioning the data into single training and a single test set. So basically we divide, then we test each division, then we combine for more accurate results. Now let's see the association rules. Retail shops are often interested in associations between different items that people buy. Say someone who buys bread is quite likely to buy milk. A person who bought the book Database System Concepts is quite likely to also buy the book Operating System Concepts. So associations information can be used in several ways. For example, when a customer buys a particular book, an online shop may suggest associated book. We are seeing these things in all the online purchasing sites like Amazon, Flipkart, etc., etc. Whenever you purchase something, the system automatically shows you associated things. So the association rules say bread is associated milk. So the DB concepts is associated to OS concepts, or OS concepts associated to networks. So left hand side is called antecedent and the right hand side is called consequent. That means bread is the antecedent and milk is the consequent. An association rule must have an associated population. The population consists of set of instances. For example, each transaction of sale at a shop is an instance and the set of all transaction is the population. Okay. So we'll have a population with each association rule. Now these rules have an associated support as well as an associated confidence. So what is support? Support is a measure of what fraction of the population satisfies both the antecedent and the consequent of the rule. For example, suppose only 0.001% of all purchases include milk and screwdrivers. The support for the rule screwdrivers is associated with milk is low. And confidence is a measure of how often the consequent is true when the antecedent is true. For example, the rule bread is associated with milk has a confidence of 80% if 80% of the purchase that included bread also include milk. Now let's see finding association rules. We are generally only interested in association rules with a reasonably high support. For example, support of 2% or greater. So to see the naive algorithm, Step 1, consider all possible sets of relevant items, and in step 2, for each set find its support, i.e. count how many transactions purchases all times in the set. Large item sets, that is the sets with a sufficiently high support. So use large item sets to generate association rules. From item set A, generate the rule A difference set B gives B or associated with B for each B belongs to A. The support of the rule is equal to support of A, and confidence of the rule is the support of A divided by support of A difference set B. Now let's see how to find support. Determine support for item sets via single pass on the set of transactions. So large item sets, again sets with a high count at the end of the pass. If memory not enough to hold all counts for all item sets, use multiple passes considering only some item sets in each pass. And optimization, once an item set is eliminated because its count or support is too small, none of its supersets needs to be considered. So the a priori technique to find large item sets. And the a priori technique for generating large item sets, only sets with single items are considered in the first pass. In the second pass, sets with the two items are considered, and so on. So first pass 1, count support of all sets with just one item, eliminate those items with low support, and in pass I or the subsequent passes, the candidates are every set of I items such that all its I minus 1 item subsets are large. So count supports of each or all candidates, and stop if there are no candidates left. At the end of a pass, all sets with sufficient supports are output as large item sets. Sets found to have too little support at the end of the pass are eliminated. Once a set is eliminated, none of its supersets needs to be considered. In other words, in pass I, we need to count only supports for sets of size I such that all subsets of the sets have been found to have sufficiently high support. It's suffices to test all subsets of size I minus 1 to ensure this property. At the end of some pass I, we would find that no sets of size I have sufficient support, so we do not need to consider any set of size I plus 1. The computation then terminates. Let's see other types of association. See, the basic association rules have several limitations that many associations are not very interesting. So deviations from the expected probability are more interesting always. For example, if many people purchase bread and many people purchase cereal, quite a few people will be expected to purchase both even if there is no connection between the two purchases. In fact, even if buying cereal has a mild negative influence on buying bread, that is, customers who buy cereal tend to purchase bread less often than the average customer. The association between cereal and bread may still have a high support. We are interested in positive as well as negative correlations between sets of items. So the positive correlation is co-occurrence is higher than predicted, whereas negative correlation is co-occurrence is lower than predicted. So sequence associations or correlations, for example, whenever bonds go up, stock prices go down in 2 days. Then we have deviations from temporal patterns are often interesting. For example, deviations from steady growth, sales of winterwear go down in summer. Okay, these things are often patterns of interest. So look for deviation from values predicted using past patterns. So mining techniques can find deviations from what one would have expected on the basis of past temporal or sequential patterns. Now let's see clustering. Clustering, intuitively finding clusters of points in the given data such that similar points lie in the same cluster, can be formalized using distance metrics in several ways. Group points into k sets for a given k such that the average distance from points from the centroid of their assigned group is minimized, where centroid is a point defined by taking average of coordinates in each dimension. Another metric is to minimize average distance between every pair of points in a cluster, and has been studied extensively in statistics but on small data sets. So data mining systems aim at clustering techniques that can handle very large data sets. For example, we have an algorithm called Birch clustering algorithm. And let's see, hierarchical clustering in the classification systems do not attempt to predict classes. Rather, they attempt to cluster related items together. For example, from biological classification, the word classification does not mean any prediction mechanism, for example. So you can classify the chordata into mammalia and reptilia, and leopards and humans comes under mammalia, while snakes and crocodiles comes under reptilia. For other examples, use internet directory services systems like Yahoo. So we have agglomerative clustering algorithms that are build small clusters, then cluster small clusters into bigger clusters, and so on. It's done like that. And we have a divisive clustering algorithm, start with all items in a single cluster and repeatedly refine or break the clusters into smaller ones. Now let's see clustering algorithm. Clustering algorithms have been designed to handle very large data sets. For example, the Birch algorithm here, main idea is to use an in-memory R tree to store points that are being clustered. Insert points one at a time into the R tree, merging a new point with an existing cluster if E is less than some delta distance away. If there are more leaf nodes that fit in memory, merge existing clusters that are close to each other. At the end of first pass, we get a large number of clusters at the leaves of the R tree. So merge clusters to reduce the number of clusters. So this is a clustering algorithm or the Birch algorithm. Let's see what. Now let's see the other types of mining. Text mining is an application of data mining textual documents. Here clusters web pages to find related pages. Cluster pages user has visited to organize their visit history. Classify web pages automatically into a web directory. We'll see in the upcoming sessions. Okay, so the data visualization systems help users examine large volumes of data and detect patterns visually. Can visually encode large amounts of information on a single screen. Then humans are very good at detecting visual patterns, so it's a useful thing. This concludes our brief exploration of the topic data mining. We'll see next time with another topic. Thank you.